Okay. So we left off here. We got Maxwell-Boltzmann to the right. Both lines represent the same molecule in a reaction at two different temperatures. Choose one color that has sufficient energy to complete a reaction at 20 degrees. We are about to get fancy. First of all, here's the activation energy, so I know it has to be past this. So, at 20 degrees, that's how many can go 20. At 40, it's a larger amount, because that's why it shifts to the right. So 40 more can do that. So, graph into words, this means as temperature increases, number of molecules increases to make a reaction happen. In your own words, explain the correlation between temperature and reaction rates. I would say as temp goes up, reaction rate usually goes up. Why? Well, more particle movement. So, more frequent collisions, more likelihood for them to be aligned, all that good stuff. Okay. Next page. Use the letters to label each of the following on the energy profiles below. A, activation energy. Well, first, I'm going to draw a line here. Both. I'll draw a line there. Draw a line here. Draw a line here. Draw a line there. I'm also going to draw a line here and there. I think that's going to help us. So for A, on this one, the activation energy is going to be from here to here. That's my activation energy. Activation energy of the reverse reaction, B, well, that's going to have to be all the way from the top to all the way at the bottom. It's kind of weird. We haven't talked about that, but that's what it looks like. C, potential energy of the forward reaction. Potential is going to be from the bottom to the reactants. D, potential energy of the reverse reaction. That's just going to be the products to the reactants. And then E, overall energy change, is your delta H. That's from reactants to products. That is your E. On this one, kind of the same idea. A, your activation energy is going to be from here to here. That's my A. My activation energy of the reverse reaction for B is going to be just from my products to my top. So that's my B. C, potential energy of the forward reaction. That's going to be reactants to 0. D, potential energy of the reverse reaction is going to be products to 0. So that's D. And overall energy change is my delta H. It's reactants to products, that is E. During the reaction, AB plus C yields BC plus A. C temporarily bonds with AB before the bond with A and B is broken. What do you call this ABC particle? Well, there's a couple things you can call it. You can call it like an activated complex, if you're talking about biology, / a transition particle. Energy profile below represents the equation AB plus C yields BC plus A. Energy profile represents X plus YZ is XZ plus Y. Label reactants, products, transition state to show the progress of the reaction along the profile. So we're going to do that on both of these. So here is my AB plus C. This would be my X plus YZ. My transition state is here, ABC. And here's where I end up with my BC plus A. Same thing over here, XYZ. Here's my XZ plus Y. So your transition state is basically at the top of the hump. So for this reaction, which has more potential energy, the products are the reactants. Well, on this one, it's going to be products. And on this one, it's going to be reactants. For each statement, true or false, the Arrhenius equation demonstrates that increasing the temperature of a reaction will lower the activation energy. False, has nothing to do with activation energy. The Arrhenius equation demonstrates that the increasing the temperature increases the overall energy change in a reaction. False. The Arrhenius equation demonstrates that increasing the temperature increases the number of collisions. True. So don't overthink that about what temperature actually does. Okay. Circle answers. Which of the following are present at the start of a reaction? At the start of a reaction, I have reactants and catalysts. In the middle, I have catalysts and intermediates. At the end, I have products and catalysts. And then here come our reaction mechanisms. So first of all, what would be the overall reaction? So cancel. So I've got 2NO. So that's going to be 2NO2 plus F2 yields, I have two of these, 2NO2F. So that means my F was an intermediate because I ended with that here and I started with it here. In a particular reaction, you propose a set of mechanisms that produces intermediate X. You conduct an experiment that tests for the presence of X, but the results are negative. X is not detected. What does that mean? So you propose a set of mechanisms that produces X. You conduct an experiment that tests for the presence of X, but the results are negative. X is not detected. What does this mean for you? This means the mechanism proposed, I cannot spell, is wrong. So the reaction is taking place. There's some kind of different steps. There must be a different intermediate. Must be a different intermediate. Three mechanisms have been proposed for the reaction in which A and B form D. So here are my three. Mechanism 1, mechanism 2, mechanism 3. Complete the following table based on the information given for each mechanism. If you have not learned how to do that, we know how to do this. So, AB slow, BC fast. First of all, molecularity. By, because I have 2 to start with. Overall reaction is going to be A plus 2B yields D. Intermediates, C was there, so that's C. Proposed rate law is only off of the slow. So rate equals K A times B. Mechanism 2. BC slow, AC fast, EA fast. Molecularity, unimolecular, by. Intermediates, so C is here, then U's, E is here, and U, so I have 2. I have C and E. Overall reaction, 2A plus B yields D. The rate law is only based off of my slow, so rate equals K, concentration of B. And my last one, B to C, that's unimolecular. A plus C is bi. C is there, then used up. So C is my intermediate. Overall reaction, A plus B yields D. Slow step, B. So rate equals K, concentration of B. Flip it. Given the following information, what is the rate law for, we're determining the rate law. The rate determining step is always the slow step. What's the rate law for this reaction? So here's my slow step, and I have no weird things here. I've got no intermediates or catalyst here, so rate is going to equal K concentration of NO2 times the concentration of F2. Okay, following data is taken from the same reaction where the reactants A and B form D. Show your work in the space below in the table. So, once again, which two trials did you use to figure out for A? So, A has to stay the same, and B has to change. So, on A, no, A has to change. So for A, I would use 2 and 3, because A is doubling, and this is not changing. So that means that means A has to be, so first of all, A was 2 and 3. For B, I would probably use 1 and 2, because B doubled from 1 and 2. And from here to here, the rate, what did that do? I have to figure out the math. I think it doubled. Yeah, that doubled. So for B, I used 1 and 2. So that means A is 0 and B is second. So what's the rate law? Rate equals KB squared. What's the value? We've done this a whole bunch of times. I'm just going to give you the answer. I'm not going to show you the work again. Rate K is going to equal 0.14 molars to -1, seconds to -1. You can do that on your own if you want to. Now look back at the proposed mechanisms on 5.7. If you have not yet determined the rate law for the mechanism, do that now. Which of those mechanisms, if any, agree with the rate law determined for the table? So rate equals KB squared. So let's go back and see if there's a B squared. Rate equals KB, AB, KB. Nope. So there has to be some kind of different mechanism. Okay. Flip it. I'll determine the rate law for the reaction below using steady state approximation. It's assumed that the concentration X, Y, Z, W remains the same. Here's my fast, here's my slow. The K1, K -1 is just like forward, backwards. We don't have to worry about that. The rate law for the above reaction is determined, once again, by the slow step. W, is it a reactant, intermediate, or product? Well, W is formed here, then used up, intermediate. The process indicated by K1 does what with W? Well, K1 is going this way, so that's going to that's going to produce W. Okay, hold on. This K1, the process indicated by K1 is going to make W, because K1 hold on, that is weird. Yeah, so my regular K, it's going to make W. It's going to make W. K to the -1 is the inverse, so it's going to go the other way. So that's going to actually use W. K2, that is going to, because it's here, it's moving forward, that's going to use W. That's kind of weird. The overall reaction rate can be stated as a change in X, Y, Z over time. Determine the rate law for this reaction. Show your work. Well, W is an intermediate, so that means, so I have my slow, W goes to Z. But I know that W is in equilibrium with X plus Y, which means X plus Y go to Z, which is my slow step. So rate equals K X. Rate equals K X times Y. So the equilibrium there was important. We've done that a whole bunch of times. Okay. Ooh, I got two humps. So the energy profile to the right represents a reaction with two steps. Which step is the fast step? Step one. How do you know? Lower activation energy. The rate determining step is step two. So like I just said, you just look at the activation energy. Higher activation energy, slow step. Lower activation energy, fast step. So on the graph, label the activation energy for all steps. So here we go. Here's my EA1. Here is my EA2. I think I drew that actually in right there. EA2. My overall change is just going to be there. That's my overall delta H, or potential energy. On the graph here, label active energy, label, okay. You're given the following mechanism. Slow, fast. What's the overreaction? Identify any intermediates. So, first of all, here's my slow. This is an intermediate. So, that means I also have this here canceling this here. So that means that NO2 gas plus CO gas yields NO gas plus CO2 gas. So my intermediate is NO3. Draw an energy profile for this mechanism. Okay. So when I have like hump, smaller hump down here, because my first step, K1, is my slow step. So it has to be the high one. So right here, here's where my NO3 would be formed. So this is going to be NO2 plus CO. And down here I'm going to have my NO plus CO2. So there's my intermediate. Comes back down, immediately used up. Okay, sweet. That was easy. Let's flip it. The overall concentration of a catalyst stays the same because you start and end with it. In May, Antarctica discovered low levels of O3 in the atmosphere. It was later discovered the problem was due to chlorofluorocarbons. This was happening in the atmosphere. Here's the equation. As the UV radiation breaks down the CFCs, a chlorine atom is produced, which breaks down ozone according to the following reaction mechanism. What is the overall reaction? Well, this is a catalyst. This is an intermediate. My overall reaction is just going to be 2O3 yields 3O2. What intermediates are formed? ClO. What's the catalyst? Cl. How do you know it's a catalyst? Well, it's in the first and last step. It's unchanged in the last step. When a catalyst is added, the activation energy is lower than with no catalyst. When a catalyst is added, the overall change in energy is the same. It's the same. If you think of our, what was I thinking of? The, like the steel wool and the battery, the amount of energy was the same, no matter with the battery or not. You just had to get it started. Okay, the graph to the right shows the elementary reaction. A catalyst is added. Draw a new reaction curve that indicates the addition of a catalyst. Easy. It's just going to be a lower hump. Everything else should be the same. So there is my lower EA. Hydrogen peroxide is a natural byproduct, so hydrogen decomposes. Here's the mechanism. The process of natural decomposition is slower. To solve this problem, your cells make a catalyst, the enzyme catalase. Catalase binds to H2O2, breaking the bond, forming an intermediate. In that space below, I'll write a new mechanism pathway for the reaction that includes catalase. Hint, there's 4 steps. Okay, you would not do this on an AP test, but let's work through it anyways. So this is going to make H2O catalase plus O. And I'm going to use up that H2O catalase to make more H2O plus catalase. Then I'm going to use my O plus H2O2 plus catalase. And that's going to give me my H2O dash catalase again, plus O2. And I'm going to use up my H2O dash catalase. And that's going to give me H2O plus catalase. Real weird. Catalase happens to be one of the fastest enzymes we know about. Just for kicks, do an internet search. How many molecules of peroxide can one catalase convert per second? Well, I'm not going to tell you. But if you do this, I will give you 1 bonus point when I'm grading this paper. That is Unit 5.